Good morning, Year 13s. Right, buddies, this is our last online lesson together for a little while. Hopefully, this is our last online lesson together, and I'll be able to see you guys actually in person next week. But today's lesson is just going to be about rigid bodies in equilibrium, which is essentially using all of that moment stuff that we did last week. So, like, guys, questions like this and force at a distance kind of thing that we did earlier on in the week. It's going to be using that just with balancing forces with F-net equations. So that's going to be our topic for today. Now I know Dr. Prow's been doing a bit of this with you in your 5th lesson, so I thought today that I was going to try to make this lesson kind of quicker. So I'm just going to do one question to give you as much possible time to practice as I possibly can. Cool, so let's do it, guys. Here we go. Okay. This is just from your textbook, and here we go. A sign is attached to a light horizontal rod of length 1 meter, which is freely hinged to a wall and supported by a light string. I'm going to start highlighting actually. And as shown in figure 4.4, which is there, 4.40. And there we go, 1 meter. And what else have we got? The sign is going to be in uniform rectangle. Which means that it's going to be the weight's going to be at the center, and its mass is 10 kilograms. So there we go. The angle of the string with the horizontal is 25 degrees, and what we're asked to find is the tension in the string. So we're after the tension in the string, number 1, and then we're also after the magnitude of the reaction force on the hinge. So that's pretty much it. Okay. So just like every question, my buddies, what you're going to want to start with is a free body diagram. So even though they've helped us a bit with this picture here, we're still going to want to redraw it on our own as a force diagram. So here we go. Get your wall going, just to show it's a wall. And here we go. We have got our lovely little bar thing there. There it is. It says that thing is 1 meter long, so let's get a different color out. And here we go. It says it's 1 meter long, so there it is. Boom, boom. What it's got on it is it's got a string up this way that attaches to the wall. Oh, it's coming into the wrong color each time, my buddies. And it's got a string coming this way which comes up and touches the wall. And that's pretty much where we are. There's a connection point there and a connection point there. Cool. So now that we've got that, what we are going to do is we're going to get our forces labeled on it, just like always, okay? So number 1, there's quite a clear force that you can see, and it's going to be that of the string. So there is a tension this way, because if you imagine what would the string do, if you could replace the string with your hand, which way would you have to pull? Well, you'd have to pull upward like that in order to not have the thing fall. So there you go. I shall call that T, and I'm going to put it just there, T. Cool. Any other forces on it? Well, yeah, there's going to be a weight. Now, because it said it was uniform, we're not going to put the weight at either end, even though they've got 2 strings attaching it as well. If it's in the picture, it's got 2 strings touching it as well. But essentially, it says it's uniform, so all of this weight is going to be pulling directly down in the center. It's kind of irrelevant information that they put these 2 strings there because they're going to be holding an equal amount each, which means that what we're going to do is have our weight directly downward like that. And there is your weight. In terms of other things that it's given, I think it told us also that there's an angle of 25 degrees. So the 25-degree angle should be in there. 25 degrees. And bish bash bosh, you've got it. Cool. Oh, actually, have we got it? Because I forgot something important. There's a hinge here. Okay, so it is actually attached to the wall there. And there's going to be forces coming out of that. Can you think of which way the forces would have to go? Here's how I do it. Imagine that this thing is not on a wall, and then think to yourself, up and down wise, so let's do vertical first. Up and down wise, would you have to pull upward or downward to keep this thing in position? Well, if you said upward, that's dead right. So we'll put an arrow straight up like that, and that is going to be a reaction force. So I'm going to actually call that RV, because it's a reaction force in the vertical. Now here's where it's tricky. Now imagine left to right on this thing here. If you're going to go left to right, which and the hinge wasn't there anymore, which way would you have to push this thing? Would you have to push it toward the right, like push against the beam, or would you have to pull into the wall? Well, if you said push against the beam this way, you're absolutely right. And that's going to be RH. Now, the reason for that is if you imagine putting your hand there, it's kind of like this bar would be smushing into your hand because of the tension in the string. So in order to prevent it from squishing your hand flat, you'd have to push right a little bit. So hopefully that's okay. Free body diagram all the way done. Now, here's why I picked this question. There's two ways of solving these guys, okay? Now, the standard way, the real way that the book usually uses is not actually my preferred way, but they kind of contrive these questions so that you have to do it that way quite a lot, and it's good to know both ways anyway. So here you go, way one. So way one is the shortest possible distance, distance to line of action of the force. Cool. So we're going to solve it doing that, okay? The shortest distance to the line of action of a force. Now, I think you've done this a bit with Dr. Proud, so I'll go kind of quick, but not super quick, just in case. Here's what I mean by line of action of the force. If you see the weight here, can you see that it's a line that's just going downward? Well, if I wanted to, what I could do is I could just extend that line infinitely in both directions. So I could go like down like this. Oops. I could go down like this past it. And I could go upward like that as well, you see. So it's an infinite line. Just the fact that the force is acting at one spot doesn't stop it from being an infinite line of force that it can travel through. So it's the same deal with the tension. So I'm going to draw this as a dashed line like that. And actually, it could continue out that way too, but that's not super relevant. Now, here we go. To start with, do we want to use forces or do we want to use moments? Well, if you think of it, we definitely want to use moments. Now, why would we want to use moments here? Well, if you look at the forces that we have, we know the weight, that's no big deal because the thing is 10 kilograms. So the weight is actually going to be, 10 times 9.8, isn't it? Or 10g, I think is sometimes you'll have learned last year, depending on who is your teacher. So the weight's 10g. So yeah, we only know this force. We don't know anything about RV. We don't know anything about RH. And we don't know anything about T. It's actually the answer. We're trying to find the tension, which means we can't use forces. There's too many unknowns. So what we're going to want to do is we're going to want to use moments. Now, we're going to want to do this. We're going to use moments, and we're going to hinge at H, which you should note. Now, that means we're going to use this spot here as our hinge, and the reason for that is, remember how it's force times a distance? Since there's two forces coming out of this cross that I've just drawn, well, the distance to those forces is 0 then, right? Which means both of these guys disappear. Happy days? Cool. Because then we can go back to regular moments, which means that anti-clockwise, so our anti-clockwise moments are going to equal our clockwise moments. So here we go. Let's start with W, because let's go anti-clockwise. Which one's going anti-clockwise? Well, T actually, if you imagine sticking your finger in here and pulling this way, this would make it go anti-clockwise because the beam would want to go upward like that. So it's the T force that we want. So it's going to be T, and here we go. This is where it's tricky. And it's going to be the shortest possible distance to the line of action of the force. So it's not going to be the 1 meter here, okay? Because it's 1 meter to get to there. But don't forget the line of action of the force is this infinite long line here. So the shortest way to get to the line of action of that force is going to be up on a perpendicular diagonal this way. Oops. So here we go. Oh, drat. Here we go. So, up like that. Can you see that this blue line, this dashy blue line, is going to be the shortest way to get to this line? I hope so. Yeah, because now look, if you check it out, so let's do a little bit of jottings here. If this whole distance here is 1 meter all the way along, So all the way along the floor, it's 1 meter. And you've got this side here, which is opposite to the 25. What you're going to get here is your distance. It's actually going to be this. It's going to be sine of 25, and I'm just going to call that d temporarily. Sine of 25 is going to equal d over, and then 1, because that's the hypotenuse, which means d is just 1 sine 25. Cool? So the shortest distance is 1 sine 25. Bish, bash, bosh. You've got it. Okay, so that's it. Clockwise then is going to be the weight. Now the weight is going to be mg, so it's 10 times 9.8, so that's mg. And then the distance to it then is going to be the shortest distance to the line of action of the force. So this line of action of the force is vertical. It's 1 meter all the way, which means that the shortest possible distance to the line of action of the force is 0. I'm struggling with the pens here for some reason. Come on, pen, change color. Oh dear. As my computer is freezing. Okay, so 0.5 is there. So that's the distance. Cool? Sweet. So, yeah, the shortest distance to it is 0.5. 0.5. And bish bash bosh. Rearrange this, my lovelies, and you should get that T is equal to 116 newtons in your calculator. Cool. That is the way that the book does it 99.9% of the time, okay? And it's a really good way, and it works really well, especially for two-dimensional shapes. So when we do laminas and stuff later on, it'll be a little bit more useful and stuff to do it this way. But there's also an easy way, which I really like, and this is components. Okay, so this is components, and this is way 2. Okay. Now, I'm giving you this just because it might be easier for you in some cases. So hinge at H. Okay, here's the difference. I'm going to switch to purple so you can see all of my work that's different in purple. And here we go. Essentially, the thing that we're concerned with is this beam, yeah? Good. Well, what we're going to want to do is resolve all of the forces to be either perpendicular or parallel with the beam. Okay, so even if it was on an angle, you'd still do perpendicular and parallel with the beam. So here you go. This is perpendicular to the beam. That's parallel with the beam. This W is perpendicular to the beam, but T is on a weird angle, right? So here's what you do. We're going to break T down into this. TV and TH. TH. If that's 25 and the whole thing's 90, then that's 65 degrees there, okay? Good. So here we go. It's the same as last time. Hinging at H, we're going to do this. Anti-clockwise is going to equal clockwise. Cool? Now, anti-clockwise. Which one's going to go anti-clockwise? Well, actually, lovelies, it's TV. So I'm going to just pop TV down. So, TV. Now, what about TH? Well, remember, we're doing this shortest distance to the line of action of the force. So TV actually has a distance that is 1 meter away, right? Because it's the entire length of the beam. But if you check it out, TH is actually acting here with the tensions. So TH's line of action actually goes through the hinge. See what I mean? Because it would be like along this way. So that's where TH would be going. And that means that it's actually 0 distance to the hinge. So TH doesn't contribute anything. Cool. So what's making it go clockwise? Well, what's making it go clockwise is W. So W is 10 times 9.8, and the shortest distance to the line of action of the force, 0.5. Cool. Now here's the only difference. Our component then, this like sine 25 malarkey, is going to come out in our TV instead. Because I bet you can see that TV is actually T, and if you check it out, it's going to be T, because that's this entire long red length, cos of 65. See what I mean? Cos 65, because what you've got is you've got your adjacent is the TV, and your hypotenuse is the T. So it's T cos 65. Cool, cool, cool. And then that's times 1, and that's still equal to all this. 10, 9.8, and 0.5. Cool beans. So all it is now, rearrangement question, gets 116 newtons again. Cool. Now, I know the way I explained it just there makes this purple way seem like it is the hard way, but I don't feel that it is usually. They're kind of maybe like for like in terms of difficulty, but I find this blue way is a bit cluttery sometimes, so The purple to me is a shortcut. If you'd like to use the shortcut, that's cool. If you don't want to use the shortcut, the blue way always works, but so does the purple way always work. So there you go. Cool. And the next one, it says find the magnitude and the direction of the reaction force on the hinge on the sine. So we're on about RV and RH there, because that's, those are the reaction forces. One pushing out and one holding it up. Cool, so let's do it. Okay, let's go blue again, and double I. Here we go. Okay, now for me, you can definitely again go moments on this again if you want, but for me, moments is the hard thing, right? And balancing equations, like doing the F-net equations, is the easy thing. So here's what I would say. Just consider both directions. So we're going to go vertical and horizontal. Well, here we go. Let's do vertical first. Vert. Define a direction to be up. Up can be positive. Define a direction to be positive, I meant. Cool. So all this is now your regular old balance of forces. So here we go. The overall force, the net force, is equal to everything pointing up, which is TV plus RV. Take away anything, and that's it. There's only just the two that are pointing upward. Take away W. Oh, there's another point for my method as well, because you would have had to break it into components anyway to do part B. So, hooray, my method. Woohoo! Okay, it's not, so F net is the only thing that ever equals MA, but it's not accelerating. It's in equilibrium. So F net is 0, which means 0 equals TV is going to be T cos 65 plus RV, which is actually what we want, take away mg, which is going to be 10 times 9.8. Cool. Now we did actually know what t was. This one's 16. So 0 equals 116 cos 65 plus RV, take away 98. Take away 98. And now it's just a calculator job. So RV equals, let's just do this mentally right now, 49.0-ish, I would say. 49.0 newtons. I certainly haven't done this ahead of you there. Cool. So that's it. That's good. So RV's done. Now all we need to get is RH. So, same deal again. This time horizontal. Hor. Define a direction to be positive. Right, but it makes no odds. F net equals, and we're just going to get, in this one, just RH, take away TH. Now, it's not accelerating, so F net is 0. 0 equals RH, take away T, and it's going to be T sine 65, which is 116 sine 65, which means RH is going to equal around 105 newtons to 3 significant figures. Yay! Oh, the beauty of having done this question before I actually showed it to you. Yay! So that's perfect. Got it. Cool. Now, here's the thing. RV and RH aren't actually, they're individual components of the reaction force, right? But they all act at that one point. So I'm going to muddy the picture right now, and I don't suggest that you do it. And I'll even use this snazzy cool pen, space pen. But RV and RH together are going to produce a force. Which one's bigger again? Is the horizontal one's bigger. So it's going to produce a force that's going to look something like this. Okay, that's the total reaction force, because it's made up of those two forces. Now, that's a bit complicated, so what I'd suggest is don't even draw that on your picture, but that's, in case you want to know the physics behind it, that's what's happening. These two forces act as one, pulling in this upward direction. But here's what we're going to do. We're just going to do this standard old way, like what you did last year. We're just going to use some Pythagoras Theorem here. So RH is 105, so draw your little RH along that way. So that's 105. The other one is 49, and that just draw them tail to tip like you always draw vectors. That's 49, which means that the reaction force, buddies, is this. And so in order to get its magnitude, like I'll just call that R, in order to get its magnitude, check it out. R is just going to be the square root of 105 squared plus 49 squared, because it's just Pythagoras' theorem. It's a right angle because it's horizontal and vertical, which means R is equal to 116 newtons when you put that in your calculator. Cool. So that's good. We now have the magnitude of it. So it said magnitude, but it also wanted, oops, I forgot to highlight that. It also said the direction. So we need to get the direction too. But that's no big deal, because check it out. In your exact same picture, let's switch to green. In your exact same picture, all you need to do is pop a little theta in there, because then you can say it's above horizontal. So I'm going to use tan. Tan theta is 49 over 105, which means theta equals, in your calculator, 25.0 approximately. 0 degrees. By God, I'm good at guessing these answers. Cool. Together, that's what makes up your final answer. Okay, so this is a proper physics question, which makes me really happy. So your final answer is this. R is going to be, the reaction force is going to be 116 newtons, and it acts in a direction of 25.0 degrees above horizontal. Okay, that is how you write it. You use that square bracket stuff to define directions, and beautiful. That's it. I would say that's a medium difficulty question. There's certainly harder questions than that, but there's certainly easier ones too. So that's what we got. Final answer all the way through. I've done that. It looks a bit tricky just because I've done a lot of workings out on this little picture, but it kind of is tricky. And I'll tell you what as well, if you can do questions like this, you can do everything. There's only so many ways of asking a question. As long as you get a perfect free body diagram and you know the strategy of hinges versus resolving, you're fine and you're flying. So I hope that's okay. There's my one model question that I was going to do with you. Feel free to look at it and stuff while you work. And here's what I'm going to get you guys to work at today. It's page 87 in your new textbooks. And it's just question 3 and 4, which I think were both okay. And then I think 6 and 7 were both nightmarish questions. But I want you to have a go at them anyway because it's good for you, and because you might get a nightmarish question on your exam, and actually all of this content is repeated in the regular maths, and so if you're able to do these hard questions, regular maths is going to feel like a triviality to you, my lovelies, when you get there, which would make me really happy. That means that we're going to get A stars if you can do stuff like that. So hooray! Question 3, 4, 6, 7, please have a go. That's it from me, and see you next week. Bye, buddies!